Hi everyone. So today we're going to get into the nuts and bolts of fossil fuels, starting with petroleum products, which is mostly what we use for gasoline. So fossil fuels, generally what we're talking about here are oil, gas, and coal. Those are the main three types that we're going to be going through in the class. These are classified as non-renewable resources because they were formed millions of years ago and there's a finite amount of them on Earth, and the rate at which we're going through them is far exceeding the rate at which they're getting replenished. They're formed through the burial and which leads to increases in pressure and temperature that tend to transform sediments into this oil and gas mixture that then migrate up through the host rocks, and we'll get into the process of how those are formed. There's different qualities that to give us some indication of the quality of the type of oil that's produced, and that depends a lot on how much money you would make if you were an oil producer. So if you have an oil that comes from a source that is particularly easier to refine, then it's going to be cheaper for you to produce that oil than if it comes from a source that is taking a lot more energy or industry in order to refine it for an end product. And then we'll talk about the production of conventional oil in the United States and how things have changed over time. And we'll get into peak oil a little bit. And then we'll talk about what is likely going to happen if we want to keep our total amount of global warming down to below a 2-degree increase in temperature. So what we have to do in terms of our consumption to cap that 2-degree temperature warming. So you'll remember this from last time we discussed the differences between renewable versus non-renewable fuels. And when we think about fossil fuels, that's going to be these three categories of non-renewable fuels, so coal, gas, and oil. Those are the ones that we're going to study today. You can see that these three fossil fuels make up the bulk of the world's energy consumption. So here, if you just look at coal, crude oil, and natural gas, I mean, it's this entire part, this wedge of the entire consumption globally. It's about 90% of the consumption in 2016. And so our dependence on fossil fuels is pretty large, and it's not likely to change in the near future to a significant degree. You can also see how over time in the United States, the type of fossil fuel being used has shifted due to supply and demand issues. So here you can see this is showing the percentage of energy consumed for different fossil fuel types. So up until the Industrial Revolution, we all used wood to heat our homes and to cook our food. But then since that Industrial Revolution, we had the onset of coal-fired energy production plants. And coal use spiked high in the 1900s and led to a lot of development in the coal industry. But in the 1930s, petroleum and natural gas, as well as some other sources of renewable energy, started to take over, and the coal production really declined through till about the mid-1970s. And so over time, these changes in the type of fossil fuel we use is largely driven by the economy, really. So you say the economy and sort of emerging technologies. So if you're a person who owns a home in 1850 and you're just fueling your home to heat it with wood, but you notice that your neighbor has just purchased a natural gas furnace, and that heats it much more efficiently, and it's this new technology that you can afford, then you'll start to purchase that as well. That causes the price of the different fuel to drop. If the price drops, even more people will start to use that technology, and it sort of leads to this ramping effect where we have switches in the type of fuel that we use depending on the sort of economical push-pull that we see. So for just looking at petroleum products, this is going to be the word that we use to describe oil. You can think of like crude oil or petroleum. A lot of times we turn this product into a gas, a liquid gas that's used in our cars. And so those terms can be used pretty loosely, but I want to clearly differentiate petroleum from natural gas, which is a totally different type of fuel that occurs in situ with oil, but is actually a gas. It's not a liquid. And we'll talk about that in a subsequent lecture. And so you remember this diagram from before. If I just hide myself briefly, you can see that we have 35.3 quads, whatever that unit is, of energy that comes from petroleum products. And the bulk of that, 25.1, which is about 82% of the total petroleum, goes into the transportation industry. So most of it is going into transportation. Which is important to understand that, these different sources of energy that we have available to us go into different sectors of our economy. And if we want to think about how we might reduce dependence on any one of these different fuels, we have to think about the impacts of these different sectors that we all rely upon. And so the basic idea with fossil fuels is that they were created millions of years ago through the conversion of plant and animal material in sediments. And so coal is shown over on the left-hand side, and oil and gas are shown here on the right-hand side. And what you see is that you get the vegetation, in terms of coal, it's dying and creating peat and bogs, and these peat bogs get compressed over time with additional pressure and heat as they get buried further and further into the Earth's surface. They metamorphose, they turn into a different kind of rock material that has a high amount of coal in it. Similarly for oil and gas, this is sort of a different scenario, only in the way that it's produced mostly from shallow ocean environments. I'm not sure why this is cut off here, but basically you have marine plants and animals that die within these shallow oceans, and they sink to the bottom of the seabed where they get buried. And then you have the same sorts of processes that are happening in both situations. You have an increase in heat, an increase in pressure as you're accumulating more and more sediment on top of these sediments, and they metamorphose, or they turn into oil and gas reserves. So I can show myself here. So we extract these reserves from the ground through multiple different means. This is a oil field that you see if you drive through West Texas, or if you're from West Texas, you see these all over the place. You can even see them locally. There's one on campus, doesn't run, but there is an old one on campus. And then we have numerous drilling rigs in the ocean and the Gulf Coast as well. If you go to the Gulf Coast, you can see these off in the distance, especially at night when their lights are shining. Coal is extracted typically through these surface mines that just dig down into them, or sometimes they have big tunnels, shaft mines, where they extract the coal through these enormous trucks. And then this is a natural gas drilling well, where they drill a big well down there and they pump that gas out. And so we take all of this, this fossil fuel out of the ground, and we use it for electricity generation or transportation or all these different means. So let's start with a discussion on oil, petroleum, right? Petroleum comes from the Latin word petra, which is rock, and oleum, which is oil. And this is why we think of petroleum as being this fossil. Fossils are, these preserved animals in rocks. So you can think of it as a fossil fuel, right? Because you can burn this stuff, it's flammable, and it's formed from fossils, fossilized animals and plants. You can create oil from petroleum, but you can also create a whole suite of other petroleum products, including jet fuels, butanes, gasolines, diesel fuels, kerosenes for camping stoves, and often we use these terms fairly interchangeably. But petroleum is actually a very complex mixture containing over 100,000, often up to 1 million different compounds. And we refer to it as this oil and gas, but when we think about it in terms of gas here, we're thinking about it as this liquid gasoline that we put into our cars, not the vaporous gas that is actually what's called natural gas that we'll talk about in the next lecture. And so this is the critter life that actually gives us our oil and gas that we use today. It's kind of crazy to think about the idea that this is all buried fossil creatures from the ocean that we're putting into our cars and burning and using to drive around the city. But that's exactly what we're doing. All of the oil and gas that we use today comes from these tiny critters that were living in the ocean millions of years ago called plankton. There's plankton currently in our ocean today. And they're tiny little microscopic plants and animals that live in the ocean. These are some pictures of zooplankton. These are animal-based plankton, but there's also plant-based plankton as well. And these plankton are just drifters. They're just really tiny little particles that, these are the plant-based ones, that just drift around in the ocean with different currents. And as they die, their skeletons and the remains fall to the bottom of the ocean where they get progressively buried with additional sediments that fall. Um, Plankton are incredibly important to the ocean. We didn't talk about them previously because they don't really have huge impacts on global climate change or huge direct impacts on global climate change, but they are a really critical part of the workings of life on our planet because they're the most common marine organism. Therefore, they're the base of the food chain in the marine system. So phytoplankton are these plant-based planktons, and then we have zooplankton would be slightly above this, it's not in here. But all these crustaceans and fish all feed on the plankton, and then these larger animals feed on the fish, including us. And so without plankton, our ocean would be virtually dead of fauna. Plankton also account for a lot of photosynthesis, about 20% of the total photosynthesis on Earth. And so they're incredibly vital to producing oxygen on Earth. So they use solar energy coming in, and they convert CO2 and nutrients into carbohydrates that become part of their shells or their bodies, plant bodies. And they respirate or photosynthesize oxygen, and that becomes part of the air that we breathe. And so they're incredibly important to the compositional makeup of our planet. But then also, as they die, they sink to the bottom where they become future carbon storage, right? We know that photosynthesis involves this respiration of CO2 into oxygen, and you store the C part, the carbon, within the body of the plant. As that plant dies, it turns into either a peat bog on land, which eventually becomes coal, or it turns into an oil deposit in the ocean when it gets buried by subsequent sediments. So they rain down to the bottom of the ocean and they settle down there into this organic mush on the seafloor. And if the accumulation rate of these plankton critters in death is really high, say it's greater than 5% even of the total sediment volume that you have accumulating on the seafloor, you can actually create what are called black shale deposits. Shale's pictured here. It's a rock type. And you can see here how there's this really stark transition between this really black shale composition and this much lighter material in the sediment above it, which has less organic matter in it. So this shale layer is one that if you could process it sufficiently, you could actually squeeze some oil and gas out of it. Because there's a huge rate of deposition of plankton material greater than 5% in the distant past. So the basic idea is that as you progressively bury these sediments, they're subjected to higher rates of pressure, higher amounts of pressure because of the overburden of sediments on top of them, and then also heat because they're being compressed. And that addition of heat and pressure causes the rocks to actually metamorphose or change their chemistry to some degree, and how the chemicals are actually bonded to one another. And so once you get to a depth of about 3 to 4 kilometers, you start to have this formation of oil where the temperatures have exceeded, what is it? I think it's 90 degrees. This is this is like 120. Yeah, it's about 190 degrees C is when you, oh no, it's 100 degrees C, sorry. So when you start to exceed 100 degrees C and you get to about 4 kilometers depth, is when you have the conditions right, the pressures and temperatures right in order for this shale rock to turn into an oil. Okay, so you initially start out with this material called kerogen. Kerogen is this geopolymer that forms around 30 degrees Celsius, and you bury that stuff an additional kilometer and you start to get oil that's formed. You can see how natural gas is formed over a much broader window, with the bulk of it formed in these kind of deeper depths than oil. But you can still have natural gas, smaller amounts of natural gas formed in shallower areas as well. So over the course of several tens of millions of years, it takes a really long time for the carbon bonds in this kerogen to break apart. This is a process that's called cracking, and this produces simple hydrocarbon molecules that we call petroleum. This is the oil that you and I use. There's also an expansion that happens in the kerogen at this stage of oil formation, and that often causes the surrounding rock or the source rock to fracture and break apart. And this allows for the oil and gas to migrate through the source rock and up to the surface where it's at a lower pressure. And this is how it makes it easy for us to extract it. So not all the oil and gas reserves that we have on our planet are at a depth of, up to 6 or greater kilometers. We don't have to drill these wells down that far because they actually create these natural fractures that then allow the fluids to migrate up to a level that it's easier to extract from. And so here's that sort of diagram. Millions of years ago, we have plankton forming. Those are falling to the bottom of the ocean and accumulating. We have additional layers of sediments and rocks put on top of those that causes increased pressure and temperatures, which leads to the formation of oil and gas. And as they form, we have expansion that happens, and that fractures the rock and allows them to migrate. And because they're less dense, they can migrate upwards above the rock. So you have trapped oil at the very top of this porous rock. If you have an impermeable rock capping that porous rock, then that's exactly where the oil will stop. And then you'll have gas on top of that. And then we mine in these wells down to these deposits and just suck them right up. Okay, next we'll be talking about what we use oil and gas for and how these deposits differ across the globe.